This section is 4.2, dealing with quadratic equations. This is a huge concept. You've done quadratics in Algebra 1, you've done them a little bit in geometry, you would have done them a fair amount in Algebra 2. This is one of those topics that just keeps coming back up. So you need to be strong with it, you need to be confident with it, and know it well. So we're supposed to be able to solve quadratic equations, and then use the discriminant to describe the roots of the quadratic. This one we're not going to do nearly so much as we are the first one. This is where you really want to emphasize your energy and understanding. That's the key thing. Now we're going to do that thing. We're going to figure out how to do that. We're going to have 3 different ways of doing it. And depending upon what's going on, the way in which you do it may be better, faster, slower. You just have to kind of decide, and we'll talk about that as we go through this. So first things first, what makes a quadratic an equation? What makes a quadratic a quadratic? And the key thing is that it's got a squared term in it. So all of these are quadratic equations that fit into this form of ax squared plus bx plus c. Any of the variables or any of the coefficients can be 0 except for the a. The a can't be 0 because if you didn't have an a, if that was 0, then there would be no x squared, and then it wouldn't be a quadratic. And what makes it a quadratic is the squared term. But it's possible, like in this one, that the b and the c could be 0. It's possible in this one the b is 0 and the c is 3. So all of these are some kind of a quadratic. So the first thing I'm going to do is talk about factoring and solving by factoring. This is the number one thing that when I sit down and talk with the Algebra 1 teachers, is the number one place where people have problems in dealing with some of the upper level math. We will be doing factoring a ton this year. We'll be doing it a ton next year. You have to be able to factor. So if what I'm about to talk about doesn't make sense to you, you need to do something about it soon, because it'll come up again and again and again. So the idea of factoring is that vocabulary. Understand, for example, if I said factor 10, you could factor it into 2 and 5. Factors are things that are multiplied together. So something multiplied together and gave me that. And so this is a trinomial, 3 terms, and if a trinomial factors, it'll factor into 2 binomials. One of the things, by the way, I don't discuss much in this section, but always try to see if there's a greatest common factor. There might be something that's in common to all 3 terms. Like both of these have a 2 in them, but there's no 2 here, so I can't factor that out. But look for that first. But let me remind you about how you multiply things together before I get to this. So like if I had x plus 3 and x minus 7, and I multiplied them together, we would, of course, FOIL. First times first is x squared. First times, the outer ones, rather, is negative 7x. The inner ones give me plus 3x. And the last ones give me negative 21. Now, almost always, don't force it, but almost always, these middle terms, the o and the I, will add together. And so this would become x squared minus 4x minus 21. When you are factoring, what you're doing is starting here and asked to go backwards. So let's start with this one. This is a quadratic equation. What makes it an equation is it's equal to 0 and it's got a squared term. So I'm going to try to solve by factoring. Now the idea here is to find the things that multiply together to give me this quadratic. So I know that if a quadratic factors, it'll factor into 2 binomials. So let's start with the f part of FOIL. First things that multiply together to give me x squared were x and x. Then I'm going to play around with the L part. Look at the options down here at the other end to get 24. You have 1 times 24, 2 times 12, 3 times 8, 4 times 6. You have to do a little bit of guessing and checking, but it's an intelligent guess and check. All of these could work in this position, but they also have to be able to work with the O and the I. So often a good rule of thumb is pick the ones that are closer together. Now also notice those 2 factors happen to be 2 units apart. So when I plug those in, knowing that I have to get a negative 24, which means one of these needs to be plus and one of these needs to be minus, what I'm looking for is what combination will give me the correct O and the I. So those inner ones multiply together and give me plus 4x, and the outer ones multiply together and give me negative 6x, and sure enough, when you add those together, you get negative 2 in the middle. So what I've done is found the factors. Now keep writing the equals 0 on the end. So chopped it off a little bit at the bottom. All I'm doing here is checking it to see if it works. So 4x minus 6x, that says negative 2x down at the bottom. So these are the right factors. Again, keep writing 0. Now let me remind you of something. If I have two things multiplied together and the answer is 0, that means one of them has to be equal to 0. The only way to multiply x times y together and get an answer of 0 is if one of those is 0. So that's the logic we use at this point. I've got x plus 4 times x minus 6 equals 0. So one of those has to be 0. Take each one, set them equal to 0. The mistake that I've seen a few people make already this year is you want to try to add the 24 over here. Well, that doesn't tell you anything. If I had x times y equals 24, that doesn't mean anything about the x or the y. I could have 4 and 6. I could have 2 and 12. There's a whole bunch of options. I could have 48 and a half. Being equal to 24 doesn't mean anything, but being equal to 0 does mean something. It means one of those factors has to be 0. So we set them equal to 0, and we solve. And what I've done is found the solutions for this quadratic equation, and I solved it by factoring. Let's look at a different way. It's called completing the square, second option. So this way, you should never solve by completing the square unless I ask you to. You should never solve by completing the square unless I ask you to, and I will. But there are reasons, because it's a terrible way to solve, but there are reasons to know how to do completing the square. And so we introduce it here because it fits with this concept, but it's not a really easy or effective way to solve a quadratic equation. So here's the logic of this. What we're going to do is try to get it so that we can solve for x. Now notice something here. When I take this equation, I'm doing a little example down here. I can factor that. That's a difference of two squares. It factors as x minus 3 and x plus 3. But I could also solve that a different way. I could add the 9 to the other side. And remember, when I solve, my final answer needs to be x equals something, and not x squared. So when I get the 9 to the other side, now I'm able to take a square root. And of course, don't forget, when you take a square root, don't forget the plus or minus. So you end up with x is equal to plus and minus 3. What made this easy to solve is x squared is a perfect square. So what I'm going to try to do is make this into a perfect square. And I'll show you what I mean here. What I'm going to do in this case is add the 24 to the other side. Now I told you not to do that before, but I'm not solving by factoring, I'm solving by completing the square. So when you do that, you take the constant to the other side and leave a little blank here. Now remember where I was going a minute ago. I had that problem, I had x squared equaled 9. Well, that's what I want to try to do. I want to be able to figure out what makes this a perfect square. I want to be able to factor that so that these two things are the same, and I could write it as one thing squared, or in other words, complete the square. Well, here's the process. To figure out what goes in this spot right here, you take this term. Now remember, in the ax squared plus bx plus c, that's a c, plus c, the b is that number right there, negative 2. So I'm going to take half of b, this is what this is saying over here, take half of b and square it. So in this case, b is negative 2, half of negative 2 is negative 1, and negative 1 squared equals 1. So what gets added here is positive 1. But the kicker is, if you add it on one side, you got to do it to the other. Now, the left-hand side will always factor if you've done this part right. And more specifically, it'll always factor as the exact same thing twice. 1 plus 24 over here is just 25. But since this is the same factor twice, instead of writing it 2 times, I can write it as one of them squared. And I've completed the square. This is now a perfect square. And the way to solve a perfect square is to get rid of the square by taking a square root. Don't forget the plus and minus when you do that. And the square root of x minus 1 squared is just x minus 1, and on the other side, plus and minus 5. And when you add this 1 to the other side, you get 6 and negative 4, just like we did the other way. Now, a lot longer, a lot more involved, but that's the logic of it. So let's try this one by completing a square. This is a little trickier, and the difference is there's a leading coefficient that's not a 1. And there's a very specific way of going about doing this. So the logic is, what we did before is we took this constant to the other side. But before I'm going to do that, I need to make the leading coefficient a 1. So whatever the a is, you're going to divide through everybody by a. So 3 divided by 3 is 1, 7 divided by 3 is 7/3, and 7 divided by 3 is 7/3 again. Now, take the constant to the other side like I did before, and figure out what gets added to both sides. It was half of b squared. Now let me remind you how you take half a number. Oh look, you put a 2 in the denominator. So half of 10, put a 2 in the denominator and you get half of 10. Well, what's half of 7/3? You put a 2 in the denominator. The great thing about math is you just follow the patterns. So half of 7/3 is 7/6. And then I need to take the 7/3, put the 2 in the denominator, square it, and I end up with 49/36. Now, nasty number. Do not do this as decimal. Do not do this as a decimal. It will be incredibly harder. Do it as fractions, and I will give you one that it's going to look like this. Do it as a fraction. So, added 49/36, added 49/36. This, on the left-hand side, will always be able to be written as the same thing twice. So what multiplied together and gave me 49/36? Well, you just saw it a second ago. It's 7/6. And what multiplies together and gives you x squared? X times x. And look what happens when you add these together. 7/6x plus 7/6x. Well, 5th grade, add, subtract fractions, that's 14/6, which reduces down to 7/3. That's supposed to be 3, which is what you're supposed to get in the middle. Now on the other side, common denominator is going to be 36, so I've got to multiply this by 12, which means I've got to multiply this guy by 12. And so 7 times 12 is 84. Add them up and you get 35/36. Write the left-hand side just as a perfect square, one thing to the second power, and then take a square root on both sides. Now, almost always, the denominator over here is going to be a perfect square. There's some weird situations where it won't, but you created that denominator when I took 7/3 and I squared it. So almost always that's going to be a perfect square. So what happens when you take that square root, you can split this fraction up as the square root of -35 over the square root of 36, and that's just going to come out as 6. Conveniently, that's what you have on the other side over here. So when I take this to the other side, it's going to let me put them together. So take the 7/6 over to the other side, -7/6, because you have common denominators, you can write it as one big fraction. Now, don't forget, when you get to this point, now we're able to deal with complex numbers. So I'm going to take the I out of that and write it in this form. So the square root of -35, the I comes out the -1 comes out as I, and then I'm going to pull this apart into separate fractions over 6. And so there's the final answer written in complex form. So last way, third option for solving a quadratic is use the quadratic formula. Now they gave this to you back in, Algebra 1 somewhere, and just said, here you go, here's a formula to learn. You need to know this. Tattoo it on you somewhere if you want. But it's got to be a permanent tattoo. If I can lick it and make it rub off, then that's cheating. But I'll let you have that out on a test. If it's a permanent tattoo, don't tell your parents I said so. So let me show you something real quickly. And this is kind of an interesting thing. And now that you are in an honors course in pre-calculus, you should be able to do this. I occasionally pop this up on a test or a quiz. I'm going to show you where the quadratic formula comes from. previously it would have just been given to you. Maybe Mrs. Bell showed you, but I'm going to run you through the logic of how you solve this equation for x. And it involves completing the square. So I'm going to solve by completing the square. So step one, of course, with completing the square was to make the leading coefficient a 1. So I need to divide everybody by a. So b gets divided by a, c gets divided by a, and a over a is just 1. Then we took the constant to the other side. So this guy goes over there, subtraction. Now I got to figure out what adds to the inside here to both sides. So we take half of the middle term. Here's that middle term. So b over a, half of it is 2a in the denominator, and then you got to square that. So the thing that gets added to both sides is b squared over 4a squared. Both sides. On the left, if you've done it right, the thing that you have here will be able to be factored. So what multiplies together gives you x squared is x times x. And the thing that you just did a second ago that multiplies together and gives you this was this thing up here before you squared it. So b over 2a, b over 2a. Now over here you have to have common denominators. So the common denominator of a and 4a squared is 4a squared. So this is missing a 4 and one more a. And so I have to put a 4, and the squaring here puts one more a, and then I do the same in the numerator. So I have a 4 and an a and the c in the numerator. So now that can be written as one thing. Now remember I subtracted this to the other side, so it's negative. So I'm just simply going to turn this around and write this as b squared minus 4ac. Sounds familiar. On the left-hand side, that of course is the same thing twice, so I can write it as one thing squared. And to get rid of the square, you're going to take a square root. Don't forget the plus and minus when you take a square root. And x plus b over 2a squared, square rooting just leaves you x plus b over 2a. 4a squared, that's a perfect square. The square root of 4a squared is 2a. Don't forget the plus and minus. And then we're going to add this constant to the other side. And notice that they have common denominators, so they'll be able to be added together and written as one big old fraction. So opposite of b plus and minus the square root of b squared minus 4ac all over 2a. Know this. I don't necessarily need for you to be able to do that. It might pop up on a quiz or something, but the final thing here you definitely need to know. Now, by the way, part of the learning objectives at the very beginning was the idea of what's called the discriminant. Well, if you take this formula and erase everything but what's underneath the square root, that's called the discriminant. And the idea is that tells you something about the kinds of answers. Because it's under a square root, if this comes out to be negative, you're going to have some complex numbers. Because it says plus or minus, what if it comes out to be 0? Well, if it's negative b plus 0 and negative b minus 0, well, that's just that answer. And what if this comes out to be a positive number? Well, then you're going to have the opposite of b plus some square root thing and the opposite of b minus some square root thing. Well, and so what you get when this thing is greater than 0, you will get 2 real zeros, what it's called, because that's what you're doing, right? When you solve for x, you were taking the quadratic and setting it equal to 0. So you're finding the zeros, or the roots of that polynomial. And if b squared minus 4ac, if the discriminant is positive, there's going to be 2 real answers. If the discriminant is equal to 0, then you just get one answer, because this is just a big old 0 over here, and you would just get that answer. So there would just be one real 0. But if what's underneath here is a negative, then you're going to end up, if what's underneath is a negative, you're going to get 2 distinct imaginary. And by distinct, I just simply mean different solutions. And the key thing there is 2. Now, keep in mind something about the quadratic formula. That plus or minus right there, it gives you 2 answers, a plus bi, a minus bi. They will always happen in what's called conjugate pairs. So, for example, if you did the quadratic formula and came up with 2 plus 3i as an answer, that would mean, because of this, 2 minus 3i would also be an answer. So let me show you what I mean with this. Let's find the zeros of this. You might try to factor it first, but 13 is a prime number, and it's just going to be 1 and 13, and you can't get a 4 out of that no matter what you try. So we're going to plug that into the quadratic. So opposite of b, plus and minus, square root of b squared minus 4 times a times c. 4 times 13 gives me 52, and when I do this subtraction, I'm going to end up with the square root of a negative. Conveniently, that's a perfect square, so the square root of negative 36 is 6i. We're going to reduce everybody by 2, factor the 2 out and cancel it, and you get 2 plus and minus 3i. So notice what I got. One answer is x equals 2 plus 3i, and the other answer is x equals 2 minus 3i. Those are conjugate pairs. Now what we're going to do is stand on our heads and do a problem similar to that, but backwards. We're going to start with the answers and see if we can get forward to the polynomial that started with this. So now look at something here. I know that x equals 3 is one of the zeros, but remember how when we started off a problem at the beginning and x minus 3 was one of the factors? Well, that meant that x equaled 3 was a root. Well, we're going backwards. So if x equals 3 is a root, that means that x minus 3 must be one of the factors. And all you're doing is adding that back over to the other side. Similarly, if x equals 2i is a root, then, well, add this back over to the other side, you're going to get x minus 2i is one of the factors. But I told you a moment ago that complex numbers always occur in what's called conjugate pairs. So if 2i is one of the zeros, if 2i is one of them, then negative 2i will also be one. So even though it's not told to you, negative 2i. And then when I bring that over to the other side, that's where I get x plus 2i. So both of these will be factors. Now this is the one that's a little trickier. So if x equals negative 1 plus 2i, I automatically know that negative 1 minus 2i will also be a root. But what's the factor? Well, just like we did before, we're just simply going to add these back over to the other side. So when I add the 1 over, I get plus 1. When I subtract the 2 over, I get negative 2i. But the conjugate, when I have x equals, so that's going to become add the 1 plus 1, add the 2i plus 2i. So notice the two pairs. The leading number, the constant doesn't change. It's the complex imaginary number part that changes. So negative 2i and plus 2i. So all of those are factors. It's a huge mess. All of these things have to multiply together to get the original thing. Notice 1, 2, 3, 4, 5. This problem is going to be an x to the 5th power with a whole bunch of other terms. And it's going to take a little while to multiply it all together. So let me show you how that happens. First of all, always, always, always do the conjugate pairs together at the same time because it'll simplify much more quickly. So I'm going to do these two blue ones together first. Now what I've got is 3 things times 3 things, so I'm going to take the x and distribute it to all 3 terms. So x times x is x squared, x times 1 is x, and x times 2i is 2ix. Now I'm going to distribute the 1 to everybody. So 1 times x is x, 1 times 1 is 1, and 1 times 2i is 2i. And then last but not least, I'm going to take this negative 2i, don't forget the negative, and distribute that. So negative 2i times x is negative 2ix, negative 2i times 1 is negative 2i, and negative 2i times positive 2i, well, negative 2 times positive 2 is negative 4, but then I times I is I squared, and I squared is negative 1, so this becomes just plus 4. Now when you do this, every single time when you multiply conjugates together, everything that's got an I will go away if you do it properly. Notice 2ix, negative 2ix. Positive 2i, negative 2i. And the I squared just became negative 1, which let this become positive 4. And so all the terms that are left That's what it simplifies to. So if you did quadratic formula on this, you would end up with those two factors, or x equals -1 plus and minus 2i. Now I'm going to do the green ones together. Save this, don't let it go away. So when I FOIL this, x times x is x squared, look what happens in the middle. Those guys cancel out. And then -2i times +2i, that would be -4i squared, and I squared is -1, so that becomes +4. Again, all the I stuff cancel out. Now, last but not least, you got to do a little bit of work here. So I got to distribute the x squared to both of those, distribute the 4 to both of those. That's what you get. Play around with that one. Now I've got to distribute this trinomial to this polynomial, and it's just a lengthy process. So look what I've done here is I take the x squared times x to the third, that's x to the fifth, then I go to this one, then I go to this one, then I go to this one. That's where I get that blue line. Then I'm going to take the 2x times every one of those, and that's where this green line comes from. And then I take the 5 times every one of those, and that's where this comes from. Now look at how I set this up. Knowing that there's going to be some like terms, I did this in columns. And so notice that in this column are all the x to the fifths, all the x to the fourths, x to the thirds, x to the seconds, x's, and the constant at the end. And it's just easier to see it, and you don't lose stuff so easily. Nasty problem. That's the final answer down there. That's the polynomial that has these roots. Big, long process. And I will give you one somewhat similar to that. Maybe not quite so long, but you'll see a problem like that for sure on a test. So here's what we had to be able to do. We had to be able to solve quadratics. I gave you 3 ways to do that. Solve by factoring, completing the square or quadratic formula, and then use the discriminant to describe the roots. And so the description is there's 1 real root, or 2 real roots, or 2 imaginary roots, or so whatever that discriminant tells you will describe the roots. Well, I hope that helps you get through this and figure out some of